So, we had been looking into the way we were constructing the arithmetic and logical unit that could support both addition and subtraction, and in the previous session we have also looked into how binary subtraction is implemented, because we have already been introduced to addition, and we also saw that how the adder circuit, or rather the full adder circuit, could also be used for implementing the subtraction operation, right. And the subtraction operation is basically we need a representation of expressing an integer x in its negative form, right. So, if we have a number x doing, let us say, a minus x is nothing but adding minus x to a, right. So, we need a representation of negative of x, which is the way we do it using a 2's complement. This is the name that we have given to that, and we have in details discussed that how this is mathematically feasible, and we saw that how it is actually x complement plus 1, right. Why and we took the inspiration from the decimal arithmetic, and we also showed you that how for a single digit number, for a 2-digit number, for a 3-digit number, this idea works, and we extended this idea in the binary domain. Instead of using the base as 10, we are using the base as 2, and did all the calculations. We showed you the circuit and so on. So, you should be able to interpret the results now. If the result is negative, please mind that it is going to be in the 2's complement form. So, yesterday, like in the last session, we have shown you the implementation of the ALU, and there we passed both positive numbers as well as negative numbers. We saw cases where the result was positive, and we also saw cases where the result was negative. So, let us try to do 1 or 2 examples like this, so that the idea is clear, and I will try to also showcase the same example in our hardware, just to convince you that whatever circuit we have designed does work, right. So, that you feel confident about it, and in the assignment you will be asked to create a very similar circuit. So, this is very good to have an understanding of how these things work, and if you have any doubts, please clarify that during the doubt clearing session. Okay. So, let us see, let us do an example. So, this example can be very trivial. Let us say we want to subtract 7 from 12, right. So, just let us say we are using 4 bits. Of course, we have 8 bits here. We can always pad the most significant bits with 0, right. But just start with a very simple example, and let us express these two numbers. So, so 12, right, in decimal is basically expressed as C, right. This is C, or maybe I will write 0xC. This is an hexadecimal representation, which is 8 and 4 is 12. So, 1 1 0 0. Okay. If you say if you want to subtract 7, right, this is 0x7, but we want to subtract, right. So, 7 could be represented as 0 1 1 1, right, but we want to do minus 7, right. So, we want to get a 2's complement of this. So, the thing that we want to write it as is going to be, if I do complement of this, which is basically the 1's complement, 1 0 0 0, right. So, I can write it as a 1's complement. Then I have to do a plus 1. So, if I do plus 1, this is going to be 1 0 0 1. Okay. So, this is going to be the 2's complement. Okay. So, then what we can do, we can take the value of 12, which is 1 1 0 0, and then add the 2's complement of 7, which is 1001, okay, and then see what happens. So, if we do plus here, 0 and 1 is 1. By the way, you should be kind of practicing this kind of things, right, and you should be able to interpret with more and more examples, right. I am going to show you one or two. So, this is 0, this is 1, right, and 1 and 1 is again 0, and then the rest is going to, you can ignore the rest of it, right, because this is kind of the output carry that goes out of the system. So, here you can see the answer is 5, but not just 5, it is plus 5, right. So, this is how you have to interpret this. The most significant bit here is being treated as 0, and this is going to be representing plus 5. Okay. The answer is basically positive. If it is indeed, if it was negative, right, we have to do something else, right. So, if we want to have an answer which is negative and you need to interpret that, mind that the answer is going to be available in the 2's complement format, and from 2's complement format you have to again do a complement of the 2's complement plus 1, which is again going to get you the signed magnitude form, right, which is basically you will get the magnitude of the data, and this is going to be a negative number. So, minus. This is we can try out just the opposite thing, right. We can try to do 7 minus 12. You should be expecting a negative answer, right, and we should also see what our adder subtractor module does. We can repeat the same exercise and see what happens. So, here we will not do minus 7, right, because we are assuming 7 minus 12. So, we will try to find out the 2's complement of 12. Okay. So, 7 is going to be remaining as it is. So, 12 is 1100. We want to find out the 2's complement. So, the 1's complement okay. So, 0 0 1 1, right. So, the 2's complement is equal to the 1's complement plus 1. So, we will basically try to add 1 to it, and 1 and 1 is 0 here, 2 basically the 1 is carried over, again 1 and 1 2. So, 0 1 carried over 1 and 0. So, we have this as whatever be it, right, we have this expression, and we are going to add this to 7. Okay. So, the 7 is now expressed as plus 7. So, this is like 1 1 1. So, we will take 0 1 1 1, and then we are going to take this as 0 1 0 0. Okay. So, what is the answer here? The answer is going to be 1 plus 0 as 1, 1 plus 0 as 1, 1 plus 1 as here this is 0, and then there is a carry 1. So, this is going to come here. Okay. So, this is the plus 7 and this is the minus 12. Of course, this is expressed in 2's complement, and this is the answer, right. Now, as you can see, the answer is like 1011, which is 11, right, is like B. That might not make sense to us, right. So, this is 0xB, right, or 11 in the decimal form. This is not minus 5. So, what you have to do here is that for a negative number, for a negative number to obtain the sign magnitude perform so the sign magnitude form, if it is, let us say I want to recover this value, and the result that I have gotten so far is R, right. So, this R is in 2's complement form. Okay. So, we have to do R inverse or basically complement of R plus 1. The same thing that we did for going from the sign magnitude to the this form, right, the same thing we are going to do here. So, is it as if we have from the decimal we do a 2's complement to go to the representation in the negative form. This is you are going back, right, you are basically again negating the negating thing, right. So, it is if it was in the 2's complement form, it is going back to the other way around, it is going to come to the decimal form, not decimal form, sign magnitude form, sorry. Okay. So, this is your R in the signed magnitude form. Okay. So, you have to perform this operation. Now, let us try to see what happens in our case. So, this is 1 0 1 1, right, and we want to do the complement of this, which is how much this complement is going to be, 0 1 0 0. Okay. So, this is the 1's complement. Okay. This is your by the way, this is your R, this is your R, and you add 1 to this. Okay. So, this is going to be 0 1 0 1. Okay. So, here you can understand that the magnitude of the number, the magnitude is equal to 5, and since this was 1 in the most significant bit, this was basically a negative number. So, that is why it is going to be negative 5. However, if you get a positive 5, you will directly get this, right, which is the result of the subtraction. The result of the subtraction, if it is positive, it is directly going to be 0 1 0 1. In this case, as you can see, I deliberately took the same example and reversed it, so that you can also see that if the answer would have been minus 5, if instead of doing 12 minus 7, I did 7 minus 12, the answer of course will be completely different, but you know this is a negative number. So, you just apply one more R inverse plus 1, that is going to give you the magnitude of the number. Okay. So, now you know that this is a, you knew here that this is a, the answer is negative, answer is negative. Okay. Now, you also knew the magnitude. So, the answer is negative, which is basically your sign, and if you do this conversion of again taking the 2's complement form, doing an inverse of that and plus 1, this is going to give you the magnitude also. So, the sign and the magnitude is recovered. So, you know, okay, the answer is minus 5. So, while we do this in our ALU, you are going to have same answer, right. So, it is just going to be 8 bits. So, we showed it for 4 bits, but there we are going to do it for 8 bits. Okay. So, while you design the ALU, you can verify with some of the calculations that we have shown here. Take some examples. You need not restrict yourself to just 4 bits, you can make it 5 or 6 bits and try out for some examples and verify them, right. You just use pen and paper and try to see what is the expected answer. You provide inputs to your ALU and try to see whether your expected answer and the output of the system matches or not, right. That is very important to verify the circuit to some extent. I am not saying that is the right way to verify or verify it exhaustively, but you are basically it will give you a basic idea of if there is any flaw in the circuit or not. Okay. In the probably if there is any issue, it is going to be showing up, right, with some examples. Okay. So, since as a part of this assignment as well as the next assignment for the last 2 weeks, right, we will be focusing more on the design and implementation of these circuits. It is very important to test a circuit once you develop or implement that. So, otherwise what happens is if you have many such circuits developed and you put them together and it does not work, right, it will be very difficult to debug what exactly went wrong, right, because this is hardware, you cannot really put printf statements here and there and track the source of the error and so on, right. So, this becomes more complicated. So, it is recommended that you keep the design as clean as possible, and whatever component that you are going to add to the system should have been tested 100% and then be integrated to the system, right. So, as an example, I can tell you that the ALU that we were making was consisting of full adders, right. So, full adder was a separately built unit and it was tested to be correct. Okay. So, you should not try to do the entire circuit in a very flat way, rather you need to make sure that the design that you are doing is quite modular, right. So, in our computer engineering or any branch of engineering, right. So, one of the main things is to handle the complexity of a system. If the system is very complex, there is a lot of different components and a lot of intricate interactions in between them, it is better to abstract out some of these things in a hierarchical way, right. So, once you understand that there is half adder, this is correct, from there you need to create a full adder, you understand this full adder is correct, right, and then you instantiate many of these full adders, right, and try to create an ALU rather than having an entirely like flat circuit and repeating the task of creating multiple full adders, because one of them you can make a mistake, right. Maybe you have made a mistake in the fifth full adder. So, do not try that, try to create modules, so that making sure that the module is correct, you should be saved from making those kind of mistakes. Okay. So, my recommendation is, while you go back to your design and implementation, follow this rule, you create a half adder, or at least the full adder is easy. So, create a full adder, right. After you create the full adder, you make copies of the tested full adder to create the ALU. Okay. So, this is very important, and once you do the ALU, we are going to also integrate this with the bus, then there could be registers, same thing with registers, right. You should not make the registers each and one every time you want to add a register. You should design the register, and that is a register module. Wherever you need to add a register module, just click and add a register module, right. In even a real world implementation where you are going to, like, people use Verilog and so on, right, for hardware design, nobody does it every time they want a new component. There is a module that you need to define for a given component and instantiate that thing, right, instantiate that class as if, right. It is very much analogous to your object oriented programming, where you have the concept of a class and you create an object, right. So, similarly you can think of this as kind of analogous to that concept, where you can have this full adder class and you instantiate let us say 8 objects of the full adder, and this 8 objects of the full adder is going to instantiate an ALU. Okay. So, keep this in mind, I will keep on giving you various hints on the assignment and how to move forward with it, but this is something that I am kind of telling upfront, that both these weeks are going to be implementation heavy, and it is better if you attend the online sessions and do doubt clarifications, right, because the things might not work if you try out at the last moment, and we are going to put quite a bit of weight in the evaluation, where we also try to design the computer to some extent, right. So, whatever we had been doing was more on the digital logic side, but there is fairly a good amount of weightage on the system design part of it, right. This is not purely a digital logic course. If you look at the name of the course, this is Foundations of Computer System Design. So, this is the last 2 or 3, maybe the last 3 weeks, right, or 3.5 weeks, what we are covering is related to computer system design. Okay. So, start implementing them as we go over the course. Okay. So, I think in the last class I have mentioned the different components being the register file, then we spoke about the ALU, then I have to talk about the control logic, and this is primarily the brain of your CPU, which controls all the or orchestrates all the data transfer and kind of operations across the components, right. This is primarily going to control which one of the components are supposed to do what at a certain point in time. And as I told you, every instruction you know what is the starting point of the instruction, that okay, there are some contents in the register and you need to do this and that, right. And you also know that what is the output, what is the final state of the system once the instruction gets executed. Okay. So, there is a starting point and there is an ending point, right. So, let us take the example again for the discussion now. Let us say I have to I have an instruction called add. Let me stick to the instruction set that we have been following for our Gajendra processor. So, add ADDR, okay. So, some address. This is our add instruction, and what it does, suppose address is whatever, right. Let us say the address that I am using here is x. So, it is going to look up the location x inside memory and add that value to the current contents of the accumulator. The instruction does not specify how it does that. Okay. You have to be kind of this is subtle, but this is a very important observation, that how it is achieved is not exposed as a part of the instruction set architecture or ISA, right. The software programmer is only going to be told that this is going to be achieved, okay. And if it affects some other registers, that has to be mentioned, because otherwise you will inadvertently lose data, right. For example, our addition is not very smart, right. The way we are trying to add is we copy the content of the memory at address location x into register B. So, whatever you have in register B is immediately lost by definition, okay, and then adding that to register A again, right. That is okay, because we are expecting the result in register A. So, that is something that has to be specified to a programmer, so that he knows or she knows that what exactly is the data that is potentially going to be lost, okay. So, either you explicitly mention everything as a part of the instruction. We had this discussion earlier also. So, if you mention everything explicitly as a part of the instruction itself, in that case you are going to spend more number of bits in the instruction and you need a bigger instruction size, right. If I have to mention that where is the source, what is the source to, what is the destination and so on, your instruction size is going to the format of the instruction, that how many bits you are expending for constructing the instruction, that is going to increase, right. If you want to shrink it, you have to have things that are already understood, okay. So, whatever we call implicit implicit understandings, right, implicit it is already as you assumed that this is going to happen. So, let me go back to our example, add ADDR. Let us say we are considering an address of x. What this thing is expected to do? Let us see. This is expected to go to memory. So, suppose this is your memory, right, and this memory in our case again is very strict about it, it's only have 16 locations. So, this x value, if it cannot be more than like 15, right, 0 to 15, that is 4 bits, right. Add is going to take up 4 bits itself, okay. So, this is add I forgot the opcode, but what we are using, I think we are using 3. So, 0 0 1 1 is going to mean that this is an add operation, okay, this is add, and then there will be 4 more bits. This is going to the be the binary equivalent of the address x, okay. So, what this is going to do, it will take the content of address x, right. So, suppose there is this content, maybe the content is the value some value, let us say 26, okay. So, this instruction is going to load this value 26 to register B. So, this 26 is going to be loaded to register B, right, because otherwise how can you do arithmetic operations, because the registers are actually hardwired right, connected to the combinational circuit of that ALU, okay. So, only after this I can do the addition, I cannot do the addition before that, right. So, there has to be a step where x is actually, or the value at x is copied to register B. Next what will happen? Next this is going to be, since it is already in register B, the ALU is getting access to this value. Before that it was not getting access, it could have been a garbage value, right. Now it is getting access, and there will be some value in register A. This value I do not know, I do not care, right, but this value is required by the ALU, because this is an implicit assumption. Again I am repeating, this is an implicit assumption that whatever was there in the accumulator, add address is going to add this value, in this case it is 26, to the accumulator. Okay. So, if you have 26 and if you have whatever value, let us say my value here is some y. Okay. So, the ALU's output, because 26 and register A and register B are connected to the ALU, the output of the ALU is going to be 26 plus y. But we are not done yet, we have promised more. Okay. The third part of the promise was that this 26 plus y number is going to be available in register A. Okay. So, the first promise is this, I mean the first thing is this, right, that it is not really something that is exposed to the outside world. I am not telling them how I am doing it. I could have also loaded it to register C, right, still it is going to do our job, right, just that the C has to be connected to ALU directly and so on. That is the part of the micro architecture that is not exposed as with the ISA, right. The ISA is happy as long as you do what you tell. Okay. So, this is loaded to register B, that was the job number 1, this job number 2 is this addition getting done, right, and job number 3 is this 26 plus y is going to be loaded to register A, loaded to register A. After this stage we are done, whatever we have promised we have achieved it, and then we can, this instructions execution is finished. Okay. And one more thing that we have to also tell, that register B is affected by this instruction. Okay. What does it mean? If you have important data inside B, register B, this is going to be lost. Okay. So, better you actually have to take the data to a different place and preserve it or put it in memory. So, now coming to the control logic part, if you think there is this sequence of steps that are, first of all there are strict sequence that is needed to be followed, and number 2 is they also have to be tightly controlled in terms of timing. Okay. You cannot really do one before the other, or you cannot, basically you cannot do that in any order, right. And you also need to know what are the minimum number of steps that has to be done before you are finished with the execution of the instruction. So, let us summarize this particular operation that we have shown you. So, the first thing that we do here is copy memory to register, right. If we copy memory to register, the values are directly available to the ALU, right. So, in the next clock, right. So, they say this is clock 1, let us say this is clock 2. In the next clock, like next clock pulse, what is going to happen? After the finishing of clock 1's trigger, the sum is calculated. You do not have to give a clock input to the ALU, because it is a combinational circuit. The combinational circuit, as long as it has the inputs available, the output is already computed. So, while you are executing clock 2, the result of addition is already there. because ALU there's full adders, the result has been computed. Okay. So, this copy memory to the registers, in this case as I told you, they do not have any control, right. So, this is direct connection, same thing, it is direct. Okay. So, in clock 2 we copy the ALU output, right, ALU output to register A. Okay. So, copy memory to register B, this was, and again copy ALU to the ALU output to register, there is no direct connection, right. The ALU cannot directly copy to register A. I do not have a this is not a bidirectional communication, this is just an output of this register A or register B that are coming to the ALU, right, that is A and B. The full adder outputs are not connected to the register. So, I have to write it to the bus, right. So, this actually means in between that ALU outputs to the bus, right, and register A inputs from the bus, then we are done. Okay. But there is one important thing that we have missed out, is that this instruction itself has to be loaded from memory. The instruction is only if I am loading the instruction from memory, then only I will know what to do. Okay. So, there will be a 0th clock, right, rather actually that will be the clock 1, clock 0 here I am mentioning. This is fetching the instruction from memory, often it is called the fetch cycle. So, what exactly we are trying to do here? The fetch cycle is governed by the program counter. The program counter indicates what instruction needs to be fetched. So, the memory address, because if you need to access memory, here in the instruction you are accessing X, because the instruction tells where to go. While you execute the program, you need a another address, because you need to know the address of the instruction itself, where is add this thing stored, right, that is going to come from the program counter. Okay. So, the program counter content is going to be the address from where we fetch the memories data, right. So, memory, but the address is going to be the program counter value. This has to be loaded to the instruction register, right. So, this value is going to be loaded to the another register, which is called the instruction register. Okay. So, there are a few things, right. The program counter does not directly come into the picture like this. The program counter writes to the bus, right. I can expand on this. We will see it very soon. The program counter writes it to the bus. There is something called the memory address register that actually does the lookup. Okay. So, this is internally implemented in a bit different way, and I will show you that very soon. So, now while I said designing of the control logic, this basically means this set of this operations, which we can call them as micro operations or micro instructions, that has to be executed in this sequence, like clock 0, clock 1, clock 2. Maybe for more complicated instructions you need more number of clocks to finish, right. So, after you finish this clock cycles, you actually get the instruction executed, and this is what is known as an instruction cycle. Okay. So, if you really look into how an instruction is executed, you may have multiple such clock cycles, right. In this case you have 1, 2, 3, 4 and let us say 5. So, this every such clock cycle some register transfer is happening, right. Some register transfer is happening, some counter is being updated, some of the values are written to the memory and so on, and you need to do this in such, of course, we want to shrink it. We do not want many clock cycles, because in that case the instruction is going to take a long time, right. So, we do not want that, we want the instruction to be finished as soon as possible. So, this is your entire thing could be called an instruction cycle. Okay. And this instruction cycle can refer to the time it takes to execute this instruction, right. Longer is the number of clock cycles inside it, longer is going to be the time taken by the instruction to get executed. Okay. So, in this one for every clock, let us say this is the 0th clock, sorry, this is the 0th clock, this is the first clock, right, this is the second clock, this is the third clock, and this is the fourth clock, and so on, right. You can think that this particular instruction is going to take 5 clock cycles, and every clock cycle the thing that happens, right, there is only one control word is going to be issued to the processor, right, in the kind of architecture that we are looking at, very simple architecture though. So, this one is a some control word is going to be issued to the processor. So, this is a control word, I will just use the word CW to refer to control word. This could be control word 0, this could be control word 1, this could be a control word 2, and so on. Okay. So, as you can see that this control word, I would also use the term which is more common, is called micro instruction to refer to the control word. Okay. Note that this is not an instruction is executed when these micro instructions get executed. Okay. So, an instruction comprises of a few micro instructions, right, and the micro instructions are something that we have kind of showed you here. Okay. This has to be of course codified in the form that the processor understands, but this is what is your micro instruction or a control word, and the sequence in which they are executed is called micro instruction sequencing. Okay. So, it is called micro instruction sequencing. It is very important because the sequence really matters. Okay. So, so now I think we kind of understood that we are going to create a series of these micro instructions in a certain sequence in order to achieve the functionality of a certain instruction. Okay. So, instead of add ADDR, you could have other things, let us say move A to B, right, that could be an instruction, and you basically need to know the micro instructions that are responsible for achieving that. Okay. So, this will basically create a multi-cycle architecture where one instruction is going to take multiple clock cycles to achieve a particular task as shown. Okay. So, we will take a look into a few control words and their sequence to have some better understanding of our system. Okay.